Good evening, Vitam. It's a pleasure to speak to you tonight about why there are phosphine molecules as illustrated here in the upper atmosphere of Venus. If we think about Venus and the Earth in size and mass and surface gravity, they're quite similar, but their evolutionary pathways have been very different, as illustrated here. And of course, we know a lot less about Venus because there's been a tiny handful of experiments that have actually made it to the surface and brought us back data, and a relatively small number of orbiters also studying the atmosphere. So what we can tell is that Venus doesn't have a magnetic field today, as shown by these abbreviations here. It doesn't have surface liquid water, and it probably does have a lot of surface volcanic activity. So compared to conditions on the Earth, where some of these promote life, it's a lot less favorable. And in particular, the surface temperature today is hundreds of degrees on Venus, and the pressure is more than 90 times what it is at the surface of the Earth. So particularly the temperature, this seems to rule out any kind of living organisms there. And we've known this for about 50 years now, since early radio observations as shown in the graph. And these literally just measure the surface of whatever layer they are sensitive to. Radio waves coming very well through the thick clouds of Venus can probe the surface. And so you can just read off the peak of that graph and find the temperature is this nearly 500 degrees centigrade. And so a decade after that diagram was made, the first and very few photos that exist were taken from the surface by a lander, confirmed it's a completely barren and baked out planetary surface. And indeed, the lander itself could only survive for about an hour, given the enormous temperatures. But the temperature in the clouds of Venus is not going to be as much. And this idea goes back even further to the 1960s, that these thick clouds of Venus could actually be a bonus from the point of view of life, because the temperature and pressure is rather similar to what they are on the surface of the Earth. So optimistically, you could say that's a kind of habitable zone for Venus. So if, and this is a big if, there was water on the early Venus, say maybe even up to about 1 billion years ago, as shown in the simulation here, then as conditions went bad, perhaps some of the smallest life forms, microbes, could have adapted to life in the clouds instead. So these clouds are rather different to what we have on Earth. The temperate zone, so-called, is much higher up than we're used to the height of our own atmosphere. But there are hypotheses that a life cycle here could work. So here's a nice review paper by Sarah Seeger and team pointing out that there could be microhabitats in the form of tiny droplets that could perhaps circulate permanently in the clouds. And so a small number of microbes could live in a droplet, a habitat only a few microns across, and be safe from falling out into the lower atmosphere and therefore being desiccated and evaporated, and perhaps against being driven upwards by winds into the upper haze. Okay, so the warning things that were perhaps not realized in the 1960s are these are very different clouds. So the acid content is extraordinarily high, at least on average. And similarly, on average, the amount of water that's there is very small. And the whole idea of life in the clouds is also very different, of course, to what we're used to thinking about life on Earth. So life in the oceans, life on the surface, life even deep in the rocks. Life in the clouds is quite a different concept. So there has never been a situation on Earth where some organism has had to face the acidity, the desiccation, and the altitude challenge all at once, because there are so many other much better habitats. So we don't know if life could actually cope in some form with all these adverse conditions. So how did this happen? This isn't really my field of science. I'm not a planetary scientist by training, but I am a radio astronomer and I'm a keen astrochemist. So I was thinking a bit about solar system observations. I was actually asked to do this as a plan for a future mission. And I was looking at molecules you can detect from space. In the solar system, phosphine is one of them. But I found that on Earth, phosphine is very much a signature of life. It is essentially only found where there are microbes in an oxygen-free environment. It's very distinctive, and it's very hard to make by any spontaneous chemical process. And I vaguely remembered this idea about Venus having oxygen-free clouds. So I wondered whether you could imagine there was some kind of phosphine-producing biosphere there, and whether that might be observable. And when I looked into it, I found, to my surprise, that there is a radio wavelength, a 1 millimeter wavelength transition of phosphine, and it will be relatively easy to observe. But because I guess nobody else kind of worked in these intersection of fields, it hadn't been done before. So with a small team starting at that point of UK scientists, we got very keen to just give this a go. So if you're not familiar with this, we're looking at rotational transitions as shown here. So the possible states of rotation that the molecule can have as it spins about its axis are limited by quantum physics to a narrow set of spin numbers, of rotation numbers. So if the molecule absorbs light, it has to jump up to a much faster speed of rotation. So when we're looking at planetary atmospheres or even exoplanetary atmospheres, most astronomers are looking at the right side of the diagram at the bottom right, at infrared wavelengths. So you can see that's actually the attenuation by absorption due to molecules in the Earth's atmosphere. There are really strongly attenuated lines due to water and carbon dioxide and molecular oxygen. But for relatively close by objects, such as in the solar system, we can exploit the left side of the diagram and also detect things like water in atmospheres, for example. And this is a real advantage because the clouds of Venus are very thick. So the infrared becomes opaque fairly near the cloud tops, but the radio and millimeter waves can escape from much lower down. So we've got a better probe of what's going on down deep into the clouds. So we can use telescopes like the Atacama Large Millimeter Array shown there to study our nearest planetary neighbor. Okay. So having had this little idea about phosphine very late in 2015, so we're now talking 8 years ago, we couldn't really start with the world's most powerful facility like ALMA, but we have some very good friends at the James Clerk Maxwell Telescope operated by the East Station Observatory. And that telescope's always been open to anyone in the world who needs a few hours of telescope time to do an interesting idea, and they will make the observations for you and send them to you. So I can highly recommend the JCMT. And although this idea was a completely crazy hypothesis, suppose there are aliens on Venus and we can see a molecule, they said, that's fine, why not try it? So they took the data for us, and we're extremely grateful for the now much wider team involved in the project. So as I said, phosphine, an anaerobic signature of life in the clouds. So the observations, it took a while to set up because it's not a technically totally easy thing to do. In fact, Venus has too much signal, so that's what we rather struggled with. The observations were made in summer of 2017, when Venus was quite close at that time. So the person who approved the use of the telescope is Jess Dempsey, who was site director at the time, and the instrument we used is a small blue cryostat in the middle of the picture. And as I say, these observations, we're very grateful to the people of the island of Hawaii for letting us use a telescope on their sacred mountain of Mauna Kea. And the JCMT in that picture is the telescope further from the camera. So we got these very difficult data, and we had proposed this saying, well, we'll just set an upper limit. We're not really expecting to find any life, but we could get an interesting upper limit that a few other astrobiologists might go, okay, well, that limits a certain kind of life or a certain amount of life in the clouds. So I poked away at this complicated data on and off, thinking, well, there's nothing there, but I'll publish it eventually. And then realized after about 18 months that actually there was a signature there. So we were all in shock at that point. And, we're thinking, what on earth do we do now? So this is the discovery spectrum. This probably, unless you're used to looking at millimeter wave spectra, this probably looks like rubbish to you. But if you make a model of phosphine in the clouds of Venus, which is the dashed line, and then process it in the ways we needed to process the data. You get the red solid line. And as you can see, that overlays the black bars, the histogram really well, and that is the actual data. So that is observed, excuse me, observed very much as a simple radiative transfer model would expect. And one of the key features is the line should be centered exactly in the middle of the window there. So there's a very, very high spectral resolution in radio and millimeter astronomy, which means we can look for the line not just at the expected wavelength, but very slightly shifted by the velocity on that night or morning of observation of Venus with respect to the telescope on the Earth. And the observation past that test is the most critical thing. The line is exactly where it should have been. Okay. So I'm slightly behind with plotting the data sets we have now, but here are the first three. And I know a lot of people are skeptical about data processing. So I think all we can do is continue to acquire data and process it in ways that are suited to new and more advanced data sets. So the ones on the left and the right are the James Clerk Maxwell Telescope data. And in response to some feedback, we've considered new methods processing, which the one on the right has. And the one in the middle is we got with director's time on the ALMA telescopes, which was very important to confirm the discovery data from JCMT. And that essentially was not done by me. I'm not an expert. It was done by staff scientists at the observatory with no skin in the game to get a biased result. And although that was a very technical observation, difficult to do for ALMA, and the processing and the calibration was very difficult, there is a clear signal there as well. So just to give an update on where we are, we have 6 epochs of observation of phosphine now, mostly in the lowest rotational transition, the 1 to 0. But independently, Martin Cordner's team observed other lines only accessible from above the ground using NASA's SOFIA airborne telescope, which you can see in the bottom picture. It's the telescope looking out the side of the aeroplane. So by flying in the stratosphere, that gets signals that are much less attenuated by the Earth's atmosphere. So there is an ongoing debate about how best to process, again, this complicated data set. But for the rotation at 4 times the speed of the original transition we were doing, my pretty simple processing on a telescope, unknown to me, I'm not a SOFIA user, has also shown a detection. And again, the key thing is exactly at the 0 offset position where it ought to be. So there's also been a lot of suggestions that the original phosphine observations we could do at the 1 millimeter line, they must have been something else, because there is a line of sulfur dioxide which is nearby in wavelength. But I think we've shown multiple times now it's not near enough, and it wouldn't have nearly enough amplitude to produce what we've seen. And we can confirm that by observations that did detect sulfur dioxide at the same time. So we can extrapolate very accurately to what would have been seen in our spectra and rule that out. And then finally, with the data in hand, all of these are observations where the planet is a single point in the telescope beam, except the ALMA ones. From that very complicated data cube, we are presently trying to figure out if there's a place on Venus where phosphine is most abundant and how we could interpret that. So my feeling at the moment, it's at the point local time essentially on Venus, if you'd been looking from Venus at the time, that the molecules are concentrated at the point where the sun was coming above the horizon from the Venus perspective. And that could be interesting from the point of view of a life interpretation, because it could be activating some microbes in the clouds by the influx of sunlight. But that's very speculative at the moment. So the final thing we're doing at the moment is, again, the Station Observatory have been very generous, and we put in a proposal with a much larger team across 9 or 10 countries to invest a larger amount of time to observe phosphine. So that's a 200-hour program. led by Dave Clements at Imperial in London. And we do have some really exciting results just about to come out from that. So the original narrow lines you saw in the spectrum would have been just that bottom red bin in the top left plot. What we're able to do now with new instrumentation and new observing modes at JCMT is look for much wider lines. And the spectrum is broadened by pressure in the atmosphere. So where you see these very much wider lines in the spectrum, that is coming from lower down, deeper into the clouds. And the spectrum is what we would expect to see because the middle bit is missing, because phosphine molecules, as they drift upwards, will be strongly attacked by sunlight. And so in the model, the red dotted spectrum, those molecules are not going to be there, which we see, but we also see a really nice fit to the wings of the spectrum, indicating the phosphine really is in the clouds. So I'm sorry about this not very well constructed plot, which I did like yesterday, but on the y-axis is altitude in kilometers going up. I've drawn roughly where the clouds are, and then abundance increases to the right of the diagram. We have simultaneous observations of water and phosphine, and we also have sulfur dioxide, and independently of that, infrared observations are being made of sulfur dioxide, particularly led by Thérèse Encrenaz's team, taking infrared spectra. So this is extremely preliminary, and I'm not an expert in atmospheric modeling, but what we're trying to do here is see if perhaps if phosphine follows other molecules that are likely produced by volcanoes, such as sulfur dioxide, or if it's different to that, and if it bears any relation to water. So if you're really keen for a life explanation, you might argue that water starts to deplete about 50 kilometers. Perhaps it's being used by organisms in some way. And then at the point where the water abundance stabilizes, the phosphine starts to be produced. So phosphine is some kind of byproduct of life. You might expect it to drift upwards from the layer where the organisms are. But I'm not committing to that viewpoint in any way. We have some wonderful confirmation from an independent team led by Rakesh Moghul. They went back and looked at data from NASA's Pioneer Venus probe, which went down through the clouds in 1978. I think the spectrometer that took these data is the largest of the silver hats in the middle of the picture on the right. And wonderfully, this team have a member of the original instrument team in the team making the new interpretation now. So that's real scientific heritage. And a signal in the mass spectrometer at mass equals 34 was originally thought, if it was there at all, to be an H2S molecule. Lots of sulfur, makes kind of sense. But Rakesh's team have found that the very similarly mass molecule phosphine, PH3, is actually a more likely interpretation of the data in the cloud zones. At 50 and 51 kilometers, we're talking about the lower clouds, the warmer, more habitable clouds there. So really fascinating confirmation of phosphine. So if we decide the phosphine is there, obviously we can't just start going, well, of course, it's some kind of life. And there's a multitude of alternative explanations. But fortunately, most of them can be at least thought about with data that exist. So the volcanism one is very exciting. The idea that phosphides from deep below the crust are thrown up through volcanic vents into the atmosphere, and then reactions with acid perhaps, excuse me, could make phosphine. This doesn't perhaps geochemically appear to work, because you'd need to loft the materials up 50 or 60 kilometers into the atmosphere through some kind of explosive volcanism. On Earth, explosive volcanism requires water, which doesn't exist on the surface of Venus. The thing that's more attackable with new observations is the idea of just abiotic chemistry in the atmosphere. Some of these routes seem thermodynamically just not going to drive in the right direction, but some of them revolve other simple chemical compounds that we can again look for with radio millimeter observations. And then the third group of this is the idea that it's a sporadic thing, perhaps a really large meteor with some phosphorus-bearing rocks was destroyed in the atmosphere, and so seeded it with ingredients that could eventually turn into phosphine. Again, a fascinating idea, but it has to have happened recently enough that probably in the space age. And so we would expect perhaps to see a meteor crater on the surface of the planet at a very young age, or perhaps even to have seen such an event with one of the orbiters, but certainly some kind of evidence which we don't see. In the wider context, there have been surprisingly few sort of experimental ways of trying to tackle this hypothetical idea of life in the clouds. But the other one that has a wealth of data is the unknown ultraviolet absorber, which appears in dark patches in Venus's atmosphere. So we get these beautiful images from the Japanese orbiter, the Akatsuki spacecraft. And some of the dark patches in the images come and go from hour to hour. So something very transient is going on, of which one hypothetical explanation could be it's something to do with a growing or decaying colony of microbes in the clouds. Obviously, other explanations are available. So phosphine, certainly not the whole story. It's something I love to do, but you know, I am equally excited about other ways of looking for life in the clouds in the most direct ways possible. So the one that's coming up soonest is the Rocket Lab Space Launch Company. Their CEO is really keen on life and Venus and space. And in combination with particularly MIT and the Breakthrough Foundation, there is a very advanced, well-advanced design to send a probe similar in size to the Pioneer Venus probe that we saw at the silver item in the picture, but to send it with modern technology down through the clouds. And the instrument will be, the one scientific instrument in a few minutes of data taking will be something that can detect if there are any compounds that fluoresce, which is also characteristic of general life processes without needing to know what kind of life it is. So the next launch window is just over a year from now. So we're really hoping that makes its launch. So just to challenge this habitat idea, lots of arguments against. So as I mentioned, the extremely high acid content in the clouds and the extremely low water content, which for the bulk, the average conditions in the cloud, you could look at the diagram on the right. So within the gray dashed ellipse, for example, let's say 20 centigrade on the red curve we think is a nice temperature for life. What would the acidity be on the blue curve? That would be nearly 100%. Please don't ask me why that curve goes under 100%. I don't understand quite the scaling. And also the partial pressure, the combination of water vapor to pressure on the green curve is extremely small. So all that's very unpromising for the clouds on average, but like on Earth, you don't expect like microbes packed shoulder to shoulder, a uniform, you know, occupancy of the clouds. That doesn't mean there can't be local conditions that do allow much more favorable droplets. And in particular, the acidity of all the droplets is not clear at all. And also, just in passing, the conditions might allow for some other solvent that's not water, which my colleague William Baines has written up an article on that in Astrobiology. However, then phosphine will be even harder to say is a byproduct of life, which we don't really know anything about. Is aerial life possible at all? Sounds kind of crazy. It does exist on the Earth. So this is a nice paper about experiments, I think with a plane flying at about 10 kilometers altitude. And they did recover live microbial cells as shown in the diagram. Not really a place where you would expect them to be living because in the Earth's atmosphere, it's very cold, but they were certainly viable, or at least some of them were. The difference is that to have a life cycle, those microbes could probably settle on a nice mountain or something on the surface of the Earth. And that's not at all going to be possible on Venus, remembering that the surface is at 100 degrees. So as I said, the idea of a biosphere completely disconnected from the ground is one that is speculative. I just wanted to show this lovely work by my student, Ben Fry, who worked with me. Well, he did all the work over the summer just to simulate what occupancy of droplets by microbes might look like. So he wrote some code that is basically a very simple game of life and allowed the dark blue cubes, which are the microbes, in a droplet to merge, for example, with another uninhabited droplet, but that might have nutrients. So he was able to show that there are certain fairly broad rules for what happens to a cell compared to the cells around it that do allow these hypothetical pixels or microbes to carry on for long times. So I took his work and tried to work out from what we know about the numbers of droplets that were measured by the descent probes, and say 50% of them are occupied or 50% of the volume is occupied. What's the maximum amount of biomass that you could have? And it comes out more than 1,000 times less than what's known on the Earth. So certainly a niche biosphere, but still an exciting possibility. And then we need to think also about whether life could ever have even started on Venus. So there are some hypotheses of just having an origin of life in the clouds, but generally work is thinking about life that started on the surface and was forced to take refuge in the clouds as the surface conditions went bad over maybe tens of millions of years. So the key difference between the Earth and Venus, as shown here in the diagram of magnetic fields as they are affected by the sun, is that the Earth has a permanent dipole magnetic field and Venus doesn't. So fast winds of protons from the sun are either deflected away from the Earth, or the protons come in at the poles of the Earth where there's very little life anyway. So we're not affected by energetic particles that ablate the ocean and the atmosphere, or corrupt the chain of atoms in DNA, for example. On Venus, that protective magnetic field doesn't exist, and so the physics is pretty different, although not entirely known. So just to compare how you might do a connected cycle of the planet as a whole, there are obviously features for the Earth on the left that don't exist on Venus. So the dynamo action, the subduction of continental plates, that doesn't exist on Venus. And so the drawdown of carbon dioxide from the atmosphere also doesn't exist on Venus. But other things do. So the erosion by the solar wind, which is much stronger, as shown on the top right of the diagram. But because of our lack of in situ data for Venus, quite a lot of the connections on the right side of the diagram, even like how much volcanism and where do the products go, is very uncertain. But there is a new era of spacecraft missions that are going to give us a lot of answers to this. So my diagram here is now a little bit incomplete because I believe China and South Korea also have missions in the planning stage. But here we have rocket labs. We have the much larger scale missions proposed by NASA and also ESA, with well-established plans to get very comprehensive data about Venus. In the case of Da Vinci, to launch another much more sophisticated descent probe. India and the United Arab Emirates have also announced plans. And some of these space agencies that are excited about Venus have the opportunity to be very agile, to send smaller missions that respond really well to current thinking and current discoveries. And I personally find it really encouraging that so many nations across the world are excited and prepared to share data and ideas. And so it is the opening up of a Venusian exploration part of the space age, again, that we've had for a long time for Mars, but we've had a really long gap for Venus. So personally, I do think this ongoing search for life is worthwhile. It's certainly fascinating to be involved with. And we can do things with very small amounts of telescope time. I think the shortest we've had is about half an hour or something, that has added really valuably to our knowledge about Venus, even if nothing to do with life it might turn out to be. So I think all these efforts are very complementary to the big explorations we're doing to investigate what's below the surface of Mars, what's going on in liquid water below the ice shells of moons like Europa, even what's going on in the hydrocarbon liquid lakes on the surface of Titan. And all these are at least conceptual extensions of habitats that do exist on the Earth, so worth looking at to see if there is some life sign there. So what are we doing next? We are, as I mentioned, we are connecting phosphine and water, see if it could fit in as part of a sensible life cycle, or if it seems completely absurd, which it does in a way, because it's a hydrogen poor habitat in the clouds. So why would you get rid of hydrogen? So that's a key thing to see if a life origin makes sense. I have to say, we don't actually know why microbes on Earth expel phosphine either, and it's also a hydrogen poor habitat in many ways where they are. So perhaps if we could get an understanding of the Earth ones, we'd have more idea what could conceptually be going on Venus. We have an observational search for ammonia, which as far as microbial organisms goes, is a better understood biosignature and could definitely have a sensible role. And we are working a lot in our team, chemists, atmospheric physicists, to try and make sure we're doing things correctly. So if the upwards diffusion speed for Venus is misunderstood, for example, and that is quite open to debate, we need to get that right. Otherwise, we won't be making the correct interpretation of possible points of origin, whether the molecules are coming from within the clouds or starting at the surface below. So yeah, I'll just put up my conclusions. Could be a small biosphere on Venus. I'm just a sort of hopeful and optimistic person about that. I'm fascinated by the idea, and I think we have a good chance of finding it. I'm equally excited about the exploration of Mars and Europa and Titan. And if we found life within the solar system, very small organisms in these harsh and expecting large complex life forms, maybe on the seas of Europa, but I think we're mostly thinking about small life forms, but there are so many exoplanets out there with much wider possibilities for biospheres, and that could be rich and full of complex life. So I'll leave with that. Thank you very much.